Hi, everyone. Can I ask you guys to stop talking, please? Thank you. I'm going to start by kind of going through this assignment a little bit. I'm not going to go through the whole thing, but I'm going to pick two of these problems or two of these polynomials and go through the whole shebang for the two polynomials. Do you guys have a preference here? These are the four polynomials that we dealt with on this, Harley? 4, okay. Add 2, okay. So that means we're going to do like 2, 6, 10, and 14. And similarly, that means we're going to do 4, 8, 12, and 16. That's basically what we're going to be answering here. Is everybody okay with that idea? Okay. So for number 2, we'll start there and just go in order. I know that was not the order you guys requested, but that's the one I'm going to do is just numeric order. I think it'll make it easier on everybody. So here, what I'm going to be concerned about are the factors of 24 and the factors of 2. So I'm going to do the factors of 24 over 1. And then I have the factors of 24 over 2. But when doing so, I get kind of a lot of duplicates. So I'm going to omit all of those duplicates. So for example, 2 over 2 reduces to 1, which is already on my list. 4 over 2 reduces to 2, already on my list, et cetera, et cetera, et cetera. All the even ones are basically duplicates. So I'm just going to list the non-duplicates there. Did I lose anybody in what I did there? I know I kind of hand-waved that a little bit. Harley? Oh, sorry. I just forgot to write that. Thank you. Absolutely is. Okay. When we move on to 6, we're going to need to look at this in our graphing calculator. So let me fire that up. I'll put it over here, I guess. Nope. I'm going to hang on to this later. I think this is my example for the notes, so I don't want to get rid of it. That's the only reason I'm going to save that for later. And just like before, I'm going to choose my window now for my graph. I'm going to pick the smallest number from that list I've just prepared and the biggest number from that list I've just prepared, and then hit graph. So I can't really get a good read as to what these are with the window that I've chosen. So I'm going to go ahead and select a different window, because I know that there's nothing going on out here that I'm interested in, and nothing going on over here that I'm interested in. So it looks like if I were to guess, this would probably be 12, so that would probably be 6. It looks like everything is captured inside -6. And this one, I don't know, that might be 1 or 2 or 3 or something, so maybe I'll just pick like 4 on the other side. Doesn't really matter as long as you're able to see everything you're supposed to. Looked like I had 3 x-intercepts that I saw when it graphed. It was just kind of too far away for me to see where they were at. So as long as I see 3 x-intercepts again, I think I'm going to be okay. So that's what I see. That does look like about 3 x-intercepts. You guys agree? Okay. So let's figure out where they are at. So here is 0. So that's -1. That's -2. It looks like we're halfway in between -1 and -2. Maybe I'll call that -1.5. Sound okay? And then there's -3, and then that one's probably -4. And then if I go to the other side, excuse me, this is again 0, so positive 1 and positive 2. It looks like we're halfway in between positive 1 and positive 2, doesn't it? So maybe that'll be positive 1.5. Everybody agree with that? Okay. What I want to do then is I want to cross-check these with my list to make sure that they are on my list, because if they're not on my list, I would not want to use them to do the synthetic divisions with. So I see negative 4 is on my list. Negative 1.5 appears to be the same as positive 3.5. And then positive 1.5 is the same as positive 3 over 2. Everybody's okay with that? So it appears that any one of these would be reasonable starting places to do my synthetic division. But which one of them would be logistically the easiest to use? Probably the negative 4. Yeah, because it's a whole number. It just makes the arithmetic a little bit easier to cope with. And that's what I would, the best reason why I would start with negative 4 here. So I'll go ahead and do my synthetic divisions. Does everybody remember how to do the synthetic division here? I'm kind of speeding through it there. Anybody need to run through how to do that again? We've done this a lot now, so I think it's fair to do that. Is that okay? Okay. So this worked. So what this tells me then is, because negative 4 gives me a remainder 0, one of my factors is x plus 4, and then the quotient is my other factor. Now I have two options. I can try to do another synthetic division, or I can try to factor the thing that's remaining. How many of us tried to do another synthetic division on this problem? Okay. When you tried to do that second synthetic division, what number did you try to use? Did you use negative 1.5 or positive 1.5? Did it work? No. No. So what is that telling you about negative 1.5? It tells you that it's an irrational solution. It's not actually negative 1.5. It's going to be some crazy decimal that's just quite close to negative 1.5. That's okay. That can happen. And in this problem, it was very hard to tell just by looking at the graph that that was not an actual solution or a rational solution, right? Because the fact that negative 1.5 is on my list made it pretty compelling that that was actually just negative 1.5. So if it doesn't work, what can you do? You can try the other one and try the synthetic division over again with positive 1.5. That should have worked. Alternatively, you could have also factored that guy by grouping. But let's use the positive 1.5. So that did work. So I still have the 1.4, or I'm sorry, the x plus 4. Because 1.5 gives me a 0 remainder, I have x plus 1.5. Oops, sorry, minus 1.5. And then this stuff gives me 2x squared minus 4. Everybody okay there? Keep in mind, if you tried doing this by grouping, the factoring here by grouping, that was fine. It's okay to do that. This was factorable by grouping. You could have done that. Okay. Now, what looks unusual about this factored form here? That factor that is x minus 1.5, typically we don't have decimals inside of our factors, right? That seems odd. Well, it turns out we can fix that and make it look a little bit nicer. If I look at the next factor or the factor next to it, 2x squared minus 4. What do you notice about 2x squared minus 4? Well, I notice that there's a greatest common factor of 2 there. Does everybody see that? So I'm going to factor the 2 out of that. And what I'm going to do is I'm going to distribute it into this one. And that gives me a much more familiar looking factored form there, where everything is an integer coefficient. Now that I have the factored form, I can just set each of these factors equal to 0 and solve. So I get negative 4. I get positive 3 over 2, which is the same thing as 1.5. If I add 2 and then square root both sides, I have to remember a plus or minus. And just as an aside, if I take the square root of 2, guess what decimal the square root of 2 is? It's about 1.41 and negative 1.41. So here's that irrational solution that we thought was negative 1.5. It turns out was really just the negative square root of 2. But I don't remember seeing a second place, or do I? If I look at this piece right here, if I zoom in very close to this, I'm going to find there's actually 2 x-intercepts there, which is kind of deceiving to me. Let's check that out real quick. So let's say we'll go from 1.3 to 1.6. And maybe go from negative 0.5 to positive 0.5. That should give us a decent picture of what's going on. So that spot that we thought at first was just one x-intercept, turned out there was 2 of them hiding there. You see now when we take a big close zoom in, would I have expected you to find those right away? No. It was not unfair to just look at that and assume there's just one thing there. Okay? What would have tipped you off, after today's lesson, we'll get some more theorems that'll give us a clue as to what's going on there to help you kind of detect that sort of a situation occurring. But as of when you did this assignment, I would not have expected anybody to realize that there could have been something weird going on. Okay. Do we feel okay on number 2 and the following problems associated with it? Okay. So let's look at 4. So for 4, the first thing I need to do is find my list of factors. So here, the leading coefficient was 1. So all I care about are the factors of the constant term. And there are a lot of factors of 108, unfortunately. That's all of them right there, Justin. Yes, sir. So once I have my list of factors, I'm going to go ahead and write in the graph or draw the graph on my calculator and take a look and see what's going on. Let's see, we have x to the 5th plus 5x to the 4th minus 5x cubed minus 45x squared plus 108. So again, I'm going to go set my window. I'm going to pick my biggest or smallest number from my list and my biggest number from my list. And I'm going to reset my y's at -10 and +10 since I changed them to do that zoom in just a moment ago. And I'm going to hit graph. So watch carefully. Did you see that little change on near the y-axis? That was the graph happening. So we couldn't tell much of what's going on from this picture clearly, so we're going to have to change our window quite substantially. So this is like 100, so that's like 50, so that'd be like 25, that would be like 10, and then like maybe that's like 5. So I'm going to try like -5 and +5, it looks like would be a reasonable guess. So if I do that, I have one x-intercept there at -3 and another x-intercept there at +2. Do you guys agree with that? Okay. So if we want to start our synthetic division, it doesn't really matter which one we start with. Let's just start with -3. That's the first one. Now, when you set up your synthetic division for this problem, you had to be pretty careful. Why did I have to write that 0 in there? Yeah, because there was no x term in my polynomial. So I'm guessing a lot of us that had problems doing the synthetic division here, I caught you with that. So again, we talked about that a lot first semester, but it's good to kind of remind ourselves that got to make sure we're checking to make sure we're including our zeros if we skip a term. So that worked. That's good. But the resulting polynomial I'm left with has 5 terms. I can't do my factoring tree on that. So let's divide again. I got a remainder 0 once again, so that's good. And now what should I do here? If I try to factor this, did anybody try to factor this result by grouping? That would have been probably what you'd have thought to do. Is this going to be factorable by grouping? No, right? If you try to do it, you're going to have what, x squared times x plus 4, and then -3x times x plus 6, and it doesn't work. So what should we do then? We'll have to do another synthetic division. What number am I going to use? What? Why negative 2? That wasn't an x-intercept. Why don't I use negative 3? It was an x-intercept. Who says they have to be used only one time? Did we ever say that? We never did, right? So that's the trick. What if we try negative 3 one more time here? That did work. Henry.
So is there anything that's zero above if this is negative 3 then?
Yep. Yep. So now let's see what we got. From this negative 3 giving me 0 remainder, I have an x plus 4, or x plus 3. From this 2 giving me a remainder 0, I have x minus 2. From this 3 giving me a remainder 0, I have an x plus 3. And then from all of this stuff, I have x squared plus x minus 6. That's factorable. If I factor that, what do I get? X plus 3 times x minus 2. So when I copy the rest of these guys down, I have this. Now this is probably not the standard way you'd write this. We'd write it this way. Now, would I expect any of us to have gotten this answer and thought to do the division with a number that you've already used again? No. Not today. Not when you're doing that homework. After today, with the notes, we're going to give you some more tools and some theorems in which you'll be able to predict when you might be able to use one of those synthetic division numbers more than once. And that'll be quite useful to us if we can just look at the graph and know whether I should be using that thing one time or more than once, right? That'd be quite valuable. All right. And then to solve on the last step, I'm going to set each of these equal to 0 and solve. So I do want 5 solutions from this, even though some of the solutions are repeated. That's okay. I do want you to list all those repeats. So we should have 5 answers, negative 3 happening 3 times, and positive 2 happening 2 times. We call this a multiplicity. Multiplicity. When that happens. So this is like x equals negative 3, multiplicity 3, because that answer happens 3 times. Is like how you would use that vocabulary. Okay. Let's talk about some more theorems, because we can, as I've hinted at, there's some more tools that we can add to this process to help us detect when some of these strange situations are afoot. So we're going to see, I don't know, like 4 or 5 theorems here today. The overall process isn't going to change. All of these theorems are really added on to the looking at the graph part and helping us make better decisions about what we're using to do the division with. So sure, if you want to call it that, that's fine. So the first one is called the fundamental theorem of algebra. And it says that all polynomial equations are solvable over the complex numbers. Not tremendously exciting. All it's saying is that all of these equations we're asking you to solve, they're all possible. They can be done. There's not any situations where you can get no solution or something weird like that happening. They're all solvable. What's more useful to us is the corollary to this. So a corollary is like a minor theorem that's really just based on a major result. And I abbreviate fundamental theorem of algebra as FTA. So we talked about this first semester when we were solving polynomials then. It basically just says the degree of the polynomial tells you the number of solutions you're looking for. Now, we have to be a little bit careful about what we mean by number of solutions, because by number of solutions we mean we're counting the repeats. So if you have like a solution that occurs like 4 times, it counts as 4 solutions. And we're counting the imaginary solutions. So if you count all of those things, then the degree tells you the number of solutions. Everybody okay there? So basically, this one is telling you like how many answers we should be looking for at the end. Well, it's nice. It's not tremendously useful. What's going to be very valuable to us is this bend, bounce, straight theorem. So for the graph of a polynomial with integer coefficients, if the x-intercept meets the x-axis with a straight, then that solution is used once. With a bounce, that solution is used an even number of times, greater than or equal to 2. And with a bend, that solution is used an odd number of times, greater than or equal to 3. So what do I mean by a bend, bounce, and straight? Well, a straight, if I look at the area around the x-intercept, looks like it's going straight through. If I look at the part of the graph around the x-intercept and it hits the x-intercept and goes back the way it came, that's a bounce. And if I look at the area around the x-intercept and the graph bends one way and then it bends the opposite direction, if it's curving like up and then it starts curving the other direction, that's like a bend. So that's what we mean by bend, bounce, and straight, is the x-intercept, the area surrounding the x-intercept of the graph looks like those three things. So I'm going to define those rather informally and just kind of draw a picture to show you what you're looking for, because that's how you're going to use this theorem. You're just going to be looking at the graph from your calculator and making some decision. So let's just go back and look at the graph that we saw earlier. This was for problem 4 from the homework. Look here at this x-intercept at -3. This is a bend, isn't it? How many times did -3 get used in our solution? 3 times. This x-intercept at +2. This is a bounce, right? How many times did that solution get used? 2 times. An even number of times for +2. An odd number of times for -3. That would have been really nice to have as a piece of information before we started doing problem 4, right? Probably all of us would have thought to try using the division more than once on that problem had we done that, or had we known this ahead of time. All right, our last 2 theorems for today. The first one is the irrational conjugates theorem. And this says for a polynomial with integer coefficients, if it has one irrational solution, actually let's say, put it this way, with integer coefficients, irrational solutions always occur in conjugate pairs. So you're always going to have even number of integer solutions. The word here that's probably we don't remember is, what do I mean by conjugate pairs? So for example, I'll just list some examples of conjugate pairs of irrational numbers. So like square root 2 and negative square root 2 are conjugates. 1 plus square root 3 and 1 minus square root 3 are conjugates. 4 minus 2 root 7 and 4 plus 2 root 7 are conjugates. I think at this point, you guys get the idea what I mean by a conjugate. They're the same except for the sign in front of the irrational part. The part that contains the radical is different. Lee? You may. Our last theorem is called the complex conjugate solutions, or conjugate theorem. This says almost the same thing. It says for a polynomial with integer coefficients, imaginary solutions always occur in conjugate pairs. And again, if we're talking about complex conjugates, like 2i and negative 2i are conjugates, or 1 plus 2i and 1 minus 2i, or 7 minus I root 3 and 7 plus I root 3. All of these are examples of conjugate pairs.
We have 40-year-old grade people on these last 4 years. Thank you.
All right, so let's do this first problem together here on this sheet, just to help get you guys going in the right direction, make sure everybody's clear as to how we're using these new theorems, okay? So number 1, part A, says to use the fundamental theorem of algebra to determine the number of solutions. So how many solutions does that polynomial equation have? Has 5. Why 5? The biggest exponent is 5. That's it. Okay. Using the rational roots theorem, create a list of possible rational solutions. What are our possible rational solutions for this going to be? It's the factors of 8 over the factors of 1, right? So just 1, 2, 4, and 8, plus or minus each of them. Everybody's okay there? It says then to use your calculator to identify likely real solutions. So that's what I had in there already. Oops. So turn off the other one, put that one in. I'll graph this from -8 to +8 because that's the biggest and smallest from my list. So what x-intercepts do you guys see on that graph? -1 and +2. Everybody agree with that? I do. Compare your answers from B and C to identify any likely irrational solutions. So what I'm doing is I'm noting that for -1, that's on my list, and for +2, that's on my list. That's everything. So would there be any irrational solutions for this? Not likely. Okay. Use the bend, bounce, straight theorem to determine the number of times each solution in part C can occur. Okay. So if I look at x equals -1, is that a bend, a bounce, or a straight? That is a bounce. So how many times could it be used? Twice, or? Yep. So 4. Okay. What else? Could it be used 8 times? How many total solutions do we have? 5, right? Could we be used 8 times then? No. So 4 is as many as we could have, right? Okay. So at x equals 2, is that a bend, bounce, or a straight? That is a bend. Good. So how many times could that one be used? 3 times, or 5 times. Could it be used more than 5 times? No, because 5 is the total number of solutions we have. Okay? So we're using the bend, bounce, straight theorem. So the bounce says it's going to be used an even number of times greater than or equal to 2. So 2 is the minimum number of times a bounce could be used, but it could also be used 4 times or 6 times or 8 times or 10 times, any even number greater than 2. But since we only have 5 solutions in this problem total, I can't have like 6, 8, 10, yada, yada, yada. I'm just capped at 2 and 4. Similarly for the bends, except it's an odd greater than or equal to 3. Cool? Got to be greater than or equal to 3. All right. So 5 says, use your answers from parts A, B, C, D, and E to make a table of possible solution sets. Okay. All right. Sorry. Whatever the letters were. But yes. Yeah, I probably misspoke. So I'm going to start by writing my x-intercepts in that I observed from my table. I want a space for my irrational stuff. I want a space for my imaginary stuff. I'm just going to abbreviate it with an I, and then a total. The total we know is always going to be 5, right? Everybody agree there? Okay. We know from above that we didn't have any irrational things because we said there are no irrational solutions from looking at the graph. Now let's fill in how many times we could use -1 and +2. So what's the minimum number of times I could use -1? 2 times. Okay. The minimum number of times I could use +2, 3 times. 2 plus 3 plus 0 is 5. Can there be any imaginaries then? No. Okay. But that's not the only combination, right? I could do 2, 5, 0. But is that possible? No, right? Because 2 plus 5 plus 0 is already bigger than 5, right? So that can't happen. What if I could have 4, 3, 0? No, okay, can't do that. And the last combination would be 4, 5, and 0. Can I do that? No. So there's really only one possibility here, that -1 is used twice and +2 is used 3 times, with no irrational solutions and no imaginary solutions. Is everybody okay with that idea? Okay. Part G says then to use synthetic division to factor the polynomial. Okay? Well, I'm just going to start with one of my zeros. Let's say -1. And how many times can I use -1? Twice, right? So that's what I'm going to do. Oops, wait a minute, what happened here? Oh, that's why. Okay, that's better. So that worked one time. I know I can use it a second time, so let's use it a second time. So that worked. Now, if I take a look, maybe that is factorable by grouping, but maybe it's not. I don't know. But what I do know is that +2 is going to be able to be used, right? So let's do another synthetic division with +2. That worked. Now, what I'm left with is a quadratic. I definitely should be able to factor that if it is factorable. But why bother? I know I can use 2 at least one more time. That worked. And what I'm left with now is just a degree 1 polynomial at the end, so there's no more factoring I need to do with that. So let's summarize what we got here. I get an x plus 1 because -1 gives me a remainder 0. I get another x plus 1 because -1 gives me a remainder 0. I get an x minus 2 because 2 gave me a remainder 0. I get another x minus 2 because 2 gave me a remainder 0. And I get another x minus 2 for that stuff at the end. So if I compact this all together into the kind of the neatest form, I'd write this as x plus 1 squared and then x minus 2 cubed. And then my last step then is to solve this factored form. So I'll just set each of these pieces equal to 0. I should have 5 answers at the end. And that's exactly what I get. So you're a quarter done with this assignment here before you've left. We did the first one together. Now I rocketed through that, but that's because I wanted to make sure I left you a little bit of time here at the end so you can try some stuff on your own. So we have about 10 minutes left. I'd encourage you to start on the next problem on your own, but you have a good exemplar to kind of compare against while you're working on doing this. Okay? Hayden. Of course.